is Pooja Bansal.
Okay, so title of my today's talk is Geometry of 10 Invariants in Statistical Work Product Manifolds. So in today's talk, I will mainly outline a brief survey of statistical work product manifold and results for curvature invariants for statistical submanifold of statistical work product manifolds. Also, we construct two new examples to support my results. So first of all, the study of differential geometry started with the geometry of submanifolds, and to study this geometry of submanifolds, it is more convenient to immerse the given manifold into a Riemannian manifold with a known geometry and then study the induced geometry of this Riemannian manifold. So as my talk is based on work product manifold, so in 1969, R.L. Bishop introduced the concept of work product manifold as a generalization of Riemannian product manifold. And in 1985, Amari introduced the statistical manifold in terms of information geometry, and such manifolds include the notion of dual connection, that is two connections, which is known as conjugate connection also. So statistical manifold is nothing but Riemannian manifold Kellen along with a couple of torsion-free affine connections nabla bar and nabla bar star, which satisfies the Kutazi equations and the equation 1. For x, y, z are any vector fields on Kellen where gamma of T Kellen is the set of all sections of tangent bundle to Kellen. Now we define the Levi-Civita connection nabla bar naught, which is defined by equation 2. And if we take this dual connections nabla bar and nabla bar star as the same connections, then our statistical manifold is known as trivial statistical manifold. Now for any statistical manifold Kellen, the difference 1-2 symmetric tensor K bar of a torsion-less affine connection nabla bar and a Levi-Civita connection nabla bar not which holds equation 4. Now next definition is for holomorphic statistical manifold. So let M be 2n-dimensional statistical manifold, a two-form ohm on M defined by ohm of xy given by g of jxy, where j is almost complex structure on M. If here this ohm is nabla parallel, then our manifold M is called holomorphic statistical manifold. And this holomorphic statistical manifold is said to be of constant holomorphic sectional curvature C if it holds equation 5. Now next definition 3 is for Kenmotsu statistical manifold. Now recently Furuhata in one of his papers studied Kenmotsu statistical manifolds and work product manifold. So first of all, we recognize the special work product manifold Kellen defined by I cross M over the warping function F, endowed with the Riemannian metric given by equation 6, where I here is any interval in the real line and delta T represents the unit vector field tangent to I. Now we have one basic result for curvature tensors R bar and R bar stars for the dualistic structure nabla bar and nabla bar star for statistical work product given by lemma 4. Now let R be statistical manifold and M be 2n-dimensional holomorphic statistical manifold of constant holomorphic sectional curvature C. Then for a statistical work product Kellen defined by R cross M over the warping function F, the curvature tensors R bar and R bar stars are given by equation 7 and equation 8 respectively. Now we define the statistical submanifolds and some terminologies based on statistical submanifolds. So let N be m-dimensional submanifold of statistical manifold Kellen, then N is said to be statistical submanifold with induced connection nabla and nabla star. The corresponding Gauss formulas are given by equation 9 and 10, in which zeta and zeta stars are bilinear mappings from which the linear transformations A mu and A mu stars are defined by equation 11 and equation 12 respectively. The corresponding Wingharton formulas are given by equation 13 and 14, where the normal dual connections nabla per and nabla star per are the Riemannian dual connections on N per. Now let R and R star be the curvature tensors of the induced connections nabla and nabla star. Then we have fundamental Gauss equations given by equation 15 and 16. Now to know the curvature of a manifold, Gauss proved the curvature of a surface by taking two-dimensional manifold, and he said the curvature of any surface can be expressed in terms of a metric. After that, later on, Riemann generalized this concept of Gaussian curvature and he gave he gave a new notion which is known as sectional curvature for Riemannian manifold. So for any orthonormal vectors x and y, the sectional curvature k on Kellen is defined by equation 17. Now its symmetric influence comes from the fact that this sectional curvature k determines the whole or the total curvature of the given manifold. So first of all, let E1 to EM and EM plus 1 to E2 and plus 1 be the standard orthonormal tangent and normal basis on n respectively. Then we define the mean curvature vector fields given by equation 18. Now we say our statistical submanifold to be totally geodesic submanifold in Kellen if our zeta, which is the second fundamental form, so if this zeta vanishes, then our submanifold is known as totally geodesic submanifold. Now the squared norm of mean curvature vector fields and second fundamental forms are given by equation 19 and 20 respectively. The scalar curvature is defined by equation 21. Now we come to our first result, basic result of my paper. So for a statistical submanifold n of a statistical warp product manifold Kellen given by I cross m over the warping function f, the expression for the scalar curvature is defined by equation 22. Also, this inequality given by 22 holds equality if and only if my submanifold n is totally geodesic with respect to the connection nabla naught, where t is the vector field tangent to n and alpha r are the smooth functions over n. Now we come to my main results, which is the chain inequality. So first result is let n be m-dimensional submanifold of a statistical warp product manifold Kellen defined by I cross m over the warping function f with tangent characteristic vector field xi. Then the chain inequality is given by equation 23 provided it holds equation 24. Now we have a direct application of this result given in theorem 7. If we take my warping function f to be the exponential function e mu, then we have a direct consequence of this result given by corollary 8. And in corollary 8, if we take my curvature c of this holomorphic statistical manifold M to be 0, that is flat manifold, then we have another corollary as an application given by corollary 9. Also in corollary 9, we have proved that my manifold R cross Cn is locally isometric to hyperbolic space H of dimension 2n plus 1 with the curvature -1. Now, before coming to the next result, which is chain inequality for Legendrian statistical submanifold of statistical warp product manifold, first of all, I will define what is Legendrian statistical submanifold. So, according to the behavior of tangent space under the action of the complex structure J, we have two special type of submanifolds known as complex or invariant submanifold, and second one is totally real or anti-invariant submanifolds. So in even dimensional case, a totally real submanifold of maximal dimension is called as Lagrangian submanifold. On the other hand, in contact case, or we can say in odd dimensional case, let n be m-dimensional submanifold of an almost contact metric manifold Kellen of odd dimension 2n plus 1, and phi be a tangent vector field maps any tangent space of n into normal space, then my submanifold n is called anti-invariant submanifold. And here, if my dimension of Kellen is 2 times of dimension of n plus 1, then the submanifold n is called Legendrian submanifold. So my next result is let n be a Legendrian statistical submanifold of statistical warp product manifold Kellen defined by I cross m over the warping function f, where I is trivial manifold here and m is holomorphic statistical manifold for normal characteristic vector field xi. Then the chain inequality is given by equation 27 provided it holds equation 28. Now similarly, we have another application of this result. If we take the warping function f to be the exponential function e mu, then we have corollary 11. And in corollary 11, if we take my curvature C of holomorphic statistical manifold to be 0, then we have the another corollary to 12. So here I have given a link for my paper, which is published in International Journal of Geometric Methods in Modern Physics. So due to lack of time, I have omitted the proof of my results. So for that, I have given this link for my paper. Now we construct two new examples to support my results. So first example is for Kenmotsu holomorphic statistical manifold. So consider C2, which is the collection of 4 tuple x1, x2, x3, x4, where xi's are real numbers. Then we define an almost complex structure J on M4 given by equation 33. Now we assume my manifold C2 as a trivial statistical manifold and R as statistical manifold. Then we define statistical warp product manifold defined by R cross C2 over the warping function F. Then this statistical manifold has a Kenmotsu holomorphic statistical structure nabla bar, whose vector fields E1, E2, E3, E4, E5 are defined by equation 34. Also on this, I have defined structure in which we define structure vector field phi, metric, and one form eta given by equations 35 and 36 respectively. Then we have these equations based on connections defined in terms of nabla bar for the vector fields E1, E2, E3, E4, and E5, which satisfies K bar given by lambda eta of x, eta of y, psi. Then we can say by my statistical bar product manifold Kellen of 5 dimension as Kenmotsu statistical manifold, where C is 0 and the Lie bracket here K bar vanishes. Now my next example is for Legendrian statistical surface. So I take 2-dimensional Legendrian statistical surface N with defined statistical 1-to symmetric tensor K of xy is equal to K bar of xy for all xy are the tangent vector fields on N. And if E1 and E2 is orthonormal frame of N2, then we have equation, we let zeta of ij defined by zeta of ei, ej, where ei, ej are the tangent vector fields. Then using Gauss formula, which is I have defined in the previous slides, we find equation 38, and this structure support my previous result or the last one, chain inequality for statistical bar product manifold. So we have here 2 examples. Construct 2 examples, one for Kenmotsu holomorphic statistical structure and the second one is for Legendrian statistical surface. Here are some references which I have used to prove my results. Thank you.
Yeah, thank you, Pooja.